as you can see here, something vibrates and makes a sound, and yeah, that's how we get waves. Class dismissed. We have an ICA next week, don't forget.
Professor, how does any of that work?
I get paid 30K for a 60-hour week. Just leave me alone. ICA next week. Goodbye.
Roasted. What's that?
2 hours later.
Alright, can I have one alcohol, please?
Yeah, can I get a beer, please? What's got you down?
Oh, it's just physics.
Physics? What about it?
I just don't understand this gosh darn standing waves.
Standing? Dude, that stuff's easy.
But wait, how do you know about physics? How do you know about...
Let me show you.
Okay, cue smooth piano music. Well, my sad physics student, at this point in your waves course, you should be familiar with the general equation for a wave, which we'll write here. In this example, we'll be considering a wave on a string of length L. Our first step is to consider our boundary conditions for a wave on a string. The first simply states that at either end of the string, at 0 and at L, the wave terminates, remembering that psi is our wave displacement. This makes sense as we deal with strings tied at both ends, for example a guitar string. The second condition states that our time derivatives of psi, i.e. the velocity of the wave, at both ends of the string must be 0. Again, this is fairly intuitive since our string must terminate at either end. What is key to note is that a standing wave is actually the sum of two waves traveling in opposite directions. When a driving force sends a wave down a string and it reaches the other end, the wave will reflect and then interfere constructively and destructively with the initial wave to create a stationary pattern. Okay, let's actually use these boundary conditions to say something useful about this wave. To do this, we'll start with a different but equivalent general wave equation, the exponential form, which you should be familiar with at this point as well. Again, just two waves traveling in opposite directions with a position and velocity. We can implement the first boundary condition at x is equal to 0, and with some simple algebra find that a is equal to minus b. We can then write our general equation for the wave with our value for the constant b. We'll first expand the brackets in the power and then use the product rule for powers to expand our terms. Then we'll take out the ae to the power I omega t as a factor. Now we need to recall Euler's theorem, which, as you've seen in your mathematics modules, relates the constant e to sine and cos functions. Using these two relations, we can simplify our wave equations to only include a single sine function with a complex coefficient. Well, that's all great, but what can we actually use this for? Well, if we go back and now implement our boundary functions, we can simplify our wave equation drastically. We see that to satisfy this condition, sine kl must be 0, which as we know will be true for integer multiples of pi. Therefore, k is equal to n pi over L. But we know that k is actually the wave number, which is equal to 2 pi over lambda. Equating the two, we are able to find an expression for the allowed wavelengths of the string, which is only dependent on the length of the string for integer values of n. And we can see this in real life. Standing waves are what make my guitar actually create sound, and with this slow-mo clip, we can start to see the string vibrate in a standing wave fashion, probably for a low value of n. To better visualize this, we can draw the first three waves for n equals 1, n equals 2, and n equals 3. We see that standing waves can only take very specific values. Nodes are located wherever the displacement is 0, and antinodes wherever displacement is at a maximum. And that's pretty much it. Any stringed instrument, as well as wind instrument, will owe its sound to the standing waves phenomenon. For a guitar player, a player can fret a string at different increments along the neck to change the length of the string and therefore the pitch of the sound that is made by the string.
See? Nothing to it.
Oh man, that was so easy. Thanks so much. I finally understand standing waves.
No problem, man.
Thank you so much.
Be free, my son.